so let's start with our today's topic, that is number system. So there are like four main number systems. The first one is decimal number system, which is our basic number system, which has a base of 10. So for example, if we have a number 4,598, we can represent it in the following way, which is 4 times 10 raised to 3 plus 5 times 10 raised to 2 plus 9 times 10 raised to 1 plus 8 times 10 raised to 0. So here you can notice that I basically used the base and raised it to some power in order to represent each of the digits from our given number. The second number system is binary number system. This system basically has a base of 2, meaning that it only has 2 possible digits, that are 0 and 1. And one example of binary number is 1011. This is a binary number, and the way we can represent it is as follows. So it can be written as 1 times 2 raised to 3 plus 0 times 2 raised to 2 plus 1 times 2 raised to 1 plus 1 times 2 raised to 0. And if I calculate this, it's just going to give me 1, which is our decimal number, or basically a number in our decimal number system. So that's how you write a binary number. Then we have the octal number system, which has a base of 8, which means that it has 8 possible digits starting from 0 up to 7. This number system normally doesn't show up on the exams. The fourth number system is the hexadecimal number system, which has a base of 16, which means it has 16 possible digit symbols. And the digits that we use for this number system starts from 0 up to 9. And then we use the letters A to F. And that adds up to a total of 16 digits. So that is the hexadecimal number system. The two main number systems that usually show up on the exam are the binary number system and the hexadecimal number system. Any questions on this? Okay, so now let's take a closer look at the binary number system. So how we would convert a binary number to a decimal number. So for example, a binary number is 10101, and the bit position is starting from right to and going to the left. It starts from 1, 2, 3, 4, and 5. How we convert a particular number is by basically adding the values of each of the bits when multiplied with the base, which are raised with the bits position. So what I mean here is basically, so we know the binary number is 10101. So यहाँ पे हम लोगों ने क्या किया? Starting with 0 index, we start raising 2 to the power of this particular bit position, and then we multiply it with the given digit, with the digit given at a particular position. So the first digit is 1 times 2 raised to 4. The second one is 0 times 2 raised to 3. Third is 1 times 2 raised to 2. Then we have 0 times 2 raised to 1. And then we have 1 times 2 raised to 0. When we compute this value, it's going to give us 16 plus 0 plus 4 plus 0 plus 1. That adds up to number 21, which is our decimal conversion of the given binary number. So इसको कैसे याद रख सकते हैं? Even though bit position is starting from 1 and goes up till n, हम लोग जब भी 2 को किसी भी power से raise करना होता है, when we are trying to convert a binary number into a decimal number, we basically raise 2 starting with number 0. So 0 से start किया up to n minus 1. So I have a couple of questions for you guys. So I'm going to give you all 4 minutes to convert these given binary numbers into their decimal equivalents. Okay, so it's time. Let's move on to our next slide. So now we want to know how we can convert a decimal to a binary number. So what we do is that we take the decimal number, we keep dividing it by 2, and we keep track of the remainders. And once we have reached a remainder of 0, then we basically, or 1, ultimately, once we know that there's no other quotient that is different from 0 or 1, then until then only we divide. And once we reach a quotient of 1 or 0, then we know that we've reached our binary number. So the digit that is at the bottom of the remainder column is called the most significant bit, because it basically tells us what it basically will help us when we're working on 2's complement, because it tells us what is the sign of that binary number. And the bit that is at the top of the remainder column is called least significant bit. And then basically just make sure you read the series of ones and zeros from bottom up. This is how you get the binary equivalent of the decimal number. So let's take an example. Take a look at an example on the next slide. So here we want to convert the decimal number 39 into a binary equivalent. So here we keep dividing 39. So when we divide 39 by 2, we get 19 as a quotient and the remainder as 1. Then we divide 19 by 2. So we get 9 and the remainder is 1. And we divide 9 by 2, we get 4, and then we get a remainder of 1. So forth. We keep doing this until we get a quotient of 1. Then we basically just divide 1 by 2, which gives us a quotient of 0, and the remainder is 1. So, and when we read this number bottom up, or this column bottom up, then we get 1 0 0 1 1 1. So that's a binary equivalent of 39. And if you want to check if whether you've converted the number correctly, then you can just do what you did. Then you can just use the approach that you applied in the previous slide to find the decimal equivalent of the binary number to verify your answer. Any questions on this? Okay, so I have these questions for you. So I would like you guys to convert the decimal numbers into their binary equivalents. Again, I'm going to giving you guys 4 minutes. Now we're going to see how we can convert other number bases to decimal. So the binary number system uses base 2. So the place values of the digits of a binary number correspond to the powers of 2. For example, the value of the binary number 10011 is determined by computing the place value of each of the digits of the number. This is exactly what you guys did in the previous slides. We can apply the same principle to any number base. So for example, if we had the number 2132 with a base 5, then how we can convert it into its decimal equivalent is just by applying the same approach. I'm just showing this as an example. It does not show up on the exam. It's just so that we know that how we can convert any number bases to decimal number system. So using the same approach, basically let's see how we can deal with hexadecimal number systems. So we know that this system uses a base of 16, which means that it has 16 possible digits starting from 0 to 9, and the remaining 6 digits are represented by A to F. So to convert a hexadecimal number into its decimal equivalent, multiply the decimal equivalent of each hexadecimal digit by the corresponding power of 16 and add the resulting values. So for example, if you're given C0E7, which is a hexadecimal number, then you basically use the same approach that we've been using to convert binary numbers into its decimal equivalent. And that's how you basically get the decimal equivalent for this hexadecimal number system as well. So how to convert a decimal to other number bases is the same approach that we used for converting a decimal number into its binary equivalent. We write the decimal number, we keep dividing it by the base, which is, for example, x, and then we make 2 columns, quotient and remainder. We keep writing the remainder values in the remainder column, and then the very last value in the remainder column is the most significant bit, and the first value in that particular column is the least significant bit. We read these numbers from the bottom up approach, and that's how you get a number equivalent to the decimal value in a different number with a different base. So for example, if we were to convert 46 to base 6, then we just use the same approach, and the decimal equivalent of, the number 46 in the decimal number system can be represented as 114 in the number system with base 6. Any questions on this? Okay, so again, now I have a couple of questions for you to try. So here are some decimal numbers and convert them in their hexadecimal equivalents. Make sure you write them down so that you can enter them in the form that I provide you later. And you guys have about 6 minutes for this, but I'm sure you guys are going to be fine and would require less than that. So your time starts now. To convert binary numbers to other number bases. So we know that 16 is equal to 2 raised to 4, which means that 4 bits of binary number can be used to describe 1 bit of a hexadecimal number. So in the following table, we see that each of the hexadecimal digit along with its equivalent decimal value and 4-digit binary sequence. So here hexadecimal digit 0 in the decimal system would be 0, and in binary number system it's going to be represented with 4 zeros. For 1 it's going to be 0001, then for 2 it's going to be 0010, and so on and so forth. Then let's take a look at the letter digits for the hexadecimal number system. So 10 is, so hexadecimal digit A basically represents the number 10 in the decimal number system, which could be represented as 1010 in binary number. B is 11, so that's 1011. Then we have C, that's 12, and binary number it's 1100. In D, it's decimal number is 13 and binary is 1101. E represents 14 and F represents 15. So to convert a binary number in its hexadecimal equivalent, normally some people might take an approach where they would want to convert the binary number first into a decimal number and then convert the decimal number into the hexadecimal form equivalent. But it's easier to do directly from binary number to its hexadecimal equivalent. What we can do here is that just divide the binary number into groups of 4 bits. And if the number of bits isn't a multiple of 4, then simply insert extra zeros to the left of the number. So for example, we have this binary number 1010010. This is the binary number. Then we break it down into groups of 4 bits. So one group will be 0101 and the second group is 0010. We basically, since this original binary number just had 7 digits, but we basically need to make groups of 4. So we just padded the entire number with zeros on the left. So ultimately, how we can convert this binary number into hexadecimal equivalent is that we convert the first group 0101 to its hexadecimal representation, that is 5. And then the second group 0010 represents 2 in the hexadecimal number system. So the final answer is 52 in the hexadecimal number system. Let's take a look at the second example, that is 1101, 1101. So we can just simply break this down into groups of 4. So the first group is 11001, second group is again 1101. So the final answer is DD with the base 16. As we saw on the previous slide, 16 is equal to 2 raised to 4. Similarly, 8 is equal to 2 raised to 3. So we know that we basically need 3 bits of binary number to write 1 bit of an octal number. So binary is also easily converted to octal number system, since octal uses a radix or a base of 8, which is a power of 2. So the representation of octal digits in binary format would be, so octal digit 0 can be represented with 3 zeros in binary. 1 will be represented as 001, 2 can be written as 010, so on and so forth, up until 7, which can be represented as 111. Any questions on this? Okay. Now, we want to see how we can convert other number bases to binary numbers. So basically using a similar approach, we can easily convert other number bases. So in order to convert a hexadecimal number into its binary equivalent, what we're going to do is that we will take each of the digits of the hexadecimal number and then substitute it with its binary notation, which is going to be a group of 4 digits. So here, let's say we have this number 3A with the base 16. So we're going to represent 3 with 4 bits, that is 0011, and then we represent A with its binary equivalent 1010. Here, A is basically representing 10 in the decimal number system, and in binary format, it's 1010. So we have a total of 8 bits in the binary number, which represents 3A. Let's take a look at the other example, E7 with the base 16. Here, we basically represent E as 1110, which is our first group, or which represents the digit E. And then the second digit 7 can be written as 0111. And when we group this together, it basically gives us the binary number. We can use the same approach when converting an octal number to a binary number. It's just that in octal number system, each of the digits can be written using 3 bits to get its binary equivalent. So for example, if we have 67 with base 8, then we write 6 as 110, and we can write 5 as 101. And when we group this and these subgroups together, then we just get the binary equivalent of 65. Similarly, if we want to write 17, we represent 1 in the octal system as 001 in the binary number system, and then we can write 7 as 111. So that's how you can basically convert hexadecimal numbers into binary equivalents without actually converting them into decimal number system and then further converting them to the binary equivalent. Any questions on this? Okay, so I have another set of questions for you to try out. So I'm just going to share the link with you all. I'm going to give you guys a total of 8 minutes to complete this.